Hi everyone, I'm Henshi Yu from the Department of Biostatistics at the University of Michigan. My presentation for Learning Meaningful Representations of Life workshop of NeurIPS 2020 is predicting unobserved cell states from disentangled representations of single-cell data using generative adversarial networks. This is joint work with Professor Joshua Welch. Let me start with the motivation. There are two main branches of deep generative models, and they have different strengths. Variational autoencoders, VAE, is able to learn disentangled representations, and the generative adversarial networks, or GAN, generally gives better samples. For single-cell data, several VAE-based methods have been used for probabilistic latent estimation, clustering, and imputation, such as SCVI and DCA, while fewer GAN-based methods are applied to single-cell data. Therefore, we propose our framework, Disentangled Representation GAN, DRGAN. We first train a VAE-based method of VAE or beta-DC-VAE to learn disentangled representations Z. Then we utilize the representations as codes to train a conditional GAN. We then have a generator network producing high-quality samples from a disentangled representation. We simulated a single-cell RNA-seq data with two pass, 20 linear or nonlinear steps, as well as 4 library size categories using the splatter R package. We then train beta-TC-VAE with 10 latent dimensions on the two simulated datasets. The latent variables are disentangled representations for the ground truth variables. We also measure disentanglement performance of different methods using mutual information gap and the Spearman correlation gap. The probabilistic PCA representations show best Spearman correlation gap, while beta-TCVE has the highest mutual information gap. We trained the VAE, beta-TCVE, and the Wasserstein GAN with gradient penalty on the Tabular-Morris dataset. We use the Tabular-Morris hard subset and the whole Tabular-Morris dataset based on random forest error and the inception score. The Wasserstein GAN with gradient penalty consistently shows higher quality than the VAE-based methods, and the beta-TCVE has the worst sample quality. We implemented our DRGAN framework on the trained beta-TCVE for the two simulated and whole Tabular-Morris datasets. The DRGAN framework gives close Spearman correlation gap values to those of beta-TCVE for the simulated datasets, and has much higher random forest errors than both VAE-based methods for the whole Tabular-Morris dataset. It means that the DRGAN combines the strengths of VAE and GAN to give high disentanglement and generation performance. We conducted latent traversals on the latent values of fibroblast cells in the whole Tabular-Morris dataset. Several latent dimensions give semantically meaningful latent traversals. For example, this rate reflects a key biological process of mesenchymal epithelial transition. It has high values for mesenchymal stem cells and fibroblasts, with a gradual transition to differentiated epithelial cell types from bladder, intestine, and pancreas, and lower values of these three. We use the DRGAN to predict unseen cell states in predicting the effects of drug treatments. We applied the latent space vector arithmetic algorithm and developed the latent space entropy as well as delta entropy to quantify the accuracy of the predicted latent values. We first randomly removed the 3 treatment cell type combinations from the training data. For DRGAN, the DRGAN random forest errors are significantly higher than those of beta-TCVE. The predictions for the unseen combinations, however, have relatively low random forest errors for both DRGAN and beta-TCVE. We found that the delta entropy is highly and negatively correlated with the difference in random forest error between DRGAN and beta TCVAE, and the delta entropy values for those unseen combinations were medium to high. Therefore, we selected and removed another 3 combinations with overall lowest delta entropy values. As expected, the DRGAN is significantly better than beta TCVAE, and both achieve high random forest error values for the unseen combinations. The green dots of the predicted cells overlap well with the blue dots of real cells for each prediction of the missing combinations. Thank you for your attention.